Okay, so this is going to be a quick demo of using the Xinu Console system to be able to write ARM assembly language and run it directly on the Raspberry Pi platform. So to start off with, I'm going to connect to the central server, Morbius. I could use any of the Systems Lab machines, but Morbius will do. I'm SSHing from a terminal already on another Linux box, but you might be connecting to Morbius via PuTTY from a Windows machine, or via the built-in SSH from a Mac laptop, or from another remote Linux machine. And I've already got SSH keys set up, so it's not going to ask me for my login and password, but normally you would log in with your login and password. I'm going to change into my COS 2200 directory that I've already in a previous week set to be not world readable. And then I'm going to make a homework 5 directory so that I can have a subdirectory for this particular project. So that's a fresh directory. There's nothing inside of there when I run ls. So for starting each assignment, we have this tar command that basically goes and opens up a package of files and makes copies of them into my fresh directory here. And this is copy pasted straight out of the assignment specification, /brilo/cos 2200 /arm playground.tgz, and it helpfully prints out those files that it's just unpacked for me, and I see a brand new directory there. It's not necessary, but I'm going to make this ARM playground. I want to move this ARM playground to another name just so that I can keep track. So if I have multiple ARM playgrounds that I'm working with, I'll be able to keep track of the 3 different problems that I'm working on. So this one will be just for the stats problem. And inside of that stats subdirectory now, I've got a main program. If I open up that up in VI, it's my standard template for getting started here. So code that I put between the start and the end comments is going to be the main program that will run when I compile and execute this. So to get started, let's do something simple. Let's print out a number. So I'm going to move into R0, the constant value, I don't know, 22, and then branch and link to printNum. PrintNum is a built-in function that I have included in this ARM Playground environment to do output. So it takes whatever integer value is stored in R0, converts that into ASCII characters, and sends those down the serial port. So this program should print the characters 2, 2. So I get my numerical output. Make, in order to compile my program. So if you have any syntax errors in your program, this is the point at which it's going to complain. It's going to say there's a problem with the assembly file, and it will direct you to which line number to look at for the problem. But this one worked just fine. So to run it on a Raspberry Pi, I run ARM console, and we'll see it go check out a backend. In this case, it got Draconian. It's powering it up. It's transferring my kernel over, and after it gives me a brief little introductory readout of the memory system, anything that comes after this series of dashes, that is my program that I just wrote. And then when it finishes my main program, the playground will say all user processes have completed. So here is the output of those 2 lines of code. I just printed out the value 22. Control spacebar and Q to get back to the command line. So that's the workflow, that's the process. You edit your main.s file, you compile it using the make command, and you run ARM console to run it, observe the values, and then control spacebar and the letter Q to quit back to the console. Repeat until done. So that's output, print number, but we also would probably like to do input for some of these. So I've also given you a helpful function called getNum, and it's going to print a question mark and a space, and then wait for you to type in digits and hit return. When that function returns, my answer is going to be in register R0. So let me change what this does here. Instead of moving 22 into R0, I'm going to add into whatever value is in R0 that comes back from getNum. I'm going to add 22 to that value. All right, so this program is going to read in a number from the user over the serial port, add 22 to that number, and then print it back out to me. All right, and remember, all of our opcodes in ARM, our 3 operand opcodes, it's destination, source, source. So this is saying store into R0 the result of adding R0 and 22. All right, let's make that. Oops, syntax error. Make ARM console. And let's see, what should we add 22 to? 57. 57 plus 22 is 79. Huzzah! All right, so that's input and output. There's one more built-in function that I want you to see here. Because our architecture lacks a divide opcode, it has a multiply, but it doesn't have a divide. If I want to divide something, well, I've given you a third function. So one for doing input, getNum, one for doing output, printNum, and one for doing simple integer division. So this time I want my program to read in a number, and then I'm going to divide that number by 5. So I'm going to move into R1, the constant value 5. R0 will already have the number that it read in from getNum. And when I call this divide opcode, this divide function, it will go and do the division using integer arithmetic. And when it returns, my quotient, the number of times that 5 goes into R0, will be in R0. It'll overwrite that. And my remainder will be in R1. So the standard calling convention tells me that whenever I call a function like printNum or divide or getNum, anything that's in registers R0, R1, or R2, or R3 could be overwritten. So if I want to have the return values from this divide be saved long enough for me to be able to print them out, I need to move them to a register R4 or above. So I'm going to copy the value of R0 onto R4, and I'm going to copy the value of R1 into R5. That way when I call printNum, so printNum is going to print the number that's in R0. It's going to print the quotient. But when I come back, R4 will still have my quotient in it if I want to do something more with it. Or I can move into R0 the remainder that I stored away in R5, and then I can print the remainder out as well. Alright, so this program is going to read in a number from me over the serial port, divide that number by 5. It's going to store the quotient and the remainder into R4 and R5 for safekeeping. Those registers are what we call non-volatile, so they'll be preserved even when I call someone else's function, which might stomp all over R0, R1, R2, and R3. And then when I come back, I'll copy that remainder back to R0, and so I'm going to print out the quotient and then print out the remainder. Make ARM console. So let's go with the number 102. So 102 divided by 5 should be 20 with a remainder of 2. And there we go. All right, so that is the workflow for our assignment this week, and those are the 3 helper functions to help you get your work done. Good luck and enjoy.